last Monday we compared two ways of representing data. One external way that looks at relationships between pairs of data items, so similarity or distance, and one so-called internal representation where we represent each single item as some kind of data structure, a vector or a set, or maybe some more complex data structures, of course. Okay, the next step is, suppose that we have these two kinds of representation. How can we use them to efficiently represent our data? And the question that I want to consider today is this. Suppose that you have a lot of data items and you want to collect together similar items. So you are considering a clustering problem. And clustering simply means this. For example, if you have some items that in some kind of representation are represented like this. For example, okay, you take two different features of a movie set, like the last time, and you plot every movie as a point in this two-dimensional plane. Well, maybe you're lucky and you find that your items are naturally grouped in this way. In this case, of course, just by looking at this graph, you find that you have three groups of items, and you call them clusters. Okay. The problem here comes when you try to define what a cluster is. For example, you can say that well, a cluster is a set where all points are similar to each other, in a sense. And but in general, to define the problem, you also need to say something about the relationship between different clusters. For example, if I just say, okay, I define a cluster as a set of very similar items, then maybe the best I can do based on this definition, so just saying that a cluster is made of very similar items, is okay, I take every item as a separate cluster. Okay. In this way, I ensure that every cluster is only made of items that are very similar to each other. What I need to add in order to make the definition more, well, let's say precise, is that different clusters should collect different items. So items in different clusters should be different from each other. So let's take these two definitions as a basic principle. We want similar items to be collected in the same cluster, and different items that are significantly different must be in different clusters. Of course, this is not a precise definition. okay, you cannot just feed that definition into a computer and hope that the computer defines 3 clusters out of this. And in fact, when we talk about clustering, we usually give some procedural definition of what clustering is. It's difficult to come up with a, a formal definition that fits every possible description, every possible situation. For example, let me say this, okay. So we said similar items should go in the same cluster, and different clusters should mean but of course different, let's say very different items. Okay, but the problem is that similarity, as you know, is a sort of transitive property. Well, not really. Consider this. You have a set made like this. I don't know, maybe a group of items here, and up here. A cloud of items here. Now, if you look at this, you will probably tend to say that here you find it, well, I should say that I see 2 clusters here. The first is a small cluster here in the center, and the second is a large cluster of points around here. Why do I say that? Because, you see, there is no solution of continuity from this point to this point. You can find a chain of very similar elements from one to the other. So it's difficult for me to divide this group of points into more than one cluster, because I should set an artificial separation at some point where 2 very close points are separated into different clusters. Okay, so, but in another sense, this, if I remove this division, okay, if I consider this cluster and this cluster, well, these properties are not valid anymore, because there are items that are very different that are collected in the same cluster. So, now this is just to say that at least for the purposes of this course, we should not try to find a very precise definition of clustering. Let's say how, in an operational sense, how we can define a procedure that, given a set of points, tries to come out with some grouping of those items, so with some with a clustering of those items. Our final purpose is, starting from lots of items, we end up with a small set of groups that we can describe more easily. So, okay, we want to find groups of items. So, maybe the most intuitive technique that we can come up with to group items is this. We have suppose that we have this distribution of points. Okay, we want to build a partition this set into clusters as I defined before. So I want to put similar items in the same set. So maybe the first thing that I can do is find the 2 points that are closest, that are nearest to each other. For example, suppose that it's these two. Okay, now I collect them in the same group. Next, once I have done this, I remain, so I started with 5 objects, okay, 5 items that I wanted to group. Now, after I collected these 2 items in the same group, I remain with 4 objects. These items, these 3 items, and this group. And I simply repeat the procedure. I find the 2 closest items in this set of 4 elements, and I group them together. For example, okay, in this case, it's these 2. Now I remain with 3 items, with 3 objects to group. This item and these 2 groups. I find the 2 closest elements, in this case it's these 2 groups, and I group them together. Finally, I remain with 2 objects. So the only way, so there are only 2 objects, they are grouped together. Let me give names to these objects. So call them 1, 2, 3, 4, and 5. So what I have done is, I started with 5 separate objects. I collected together the 2 most similar objects. And I repeated the procedure. 2 and 3 were collected together. Then the 2 objects were collected together, and finally I got this. Okay. Now, what is the clustering here? Well, here, what I actually created is a set of possible meanings of the word clustering for this particular set. So, for example, I can decide that I'm fine with 3 groups. Then I simply stop the procedure here, where I have 3 groups: 1, 2, 3, and 4, 5. Or maybe I find with 2 groups. Then the best candidate for having 2 groups is 1 and 2, 3, 4, 5. Now, of course, I'll try to be a little more precise about this. So, the basic idea is this. Okay, I start with, let's say, as many clusters as there are items. So, every item is its own cluster, and then I join the 2 closest clusters into one. Clusters that only contain 1 element are called singleton. So I start with all singletons and I merge them by always merging the 2 closest clusters. Of course, in this drawing, it's difficult to see that 2 and 3 are slightly more different. Let's say, okay, 2 and 3 are like this. So it's easier to see. Okay, here, well, we have a, you see, this algorithm works as long as we have a definition of distance or of similarity between 2 elements. Okay, and in this case, for example, I consider the distance as drawn on this blackboard. Okay, so 4 and 5 are very similar because they are very close. 1 is very different from all the others because it's far from them. Of course, we can adapt this procedure to any definition of similarity of distance. Okay, so we can also try to write a sketch of this of the algorithm. What about the other lights?
Maybe from
The other. Okay, I'm going to try. No.
Yeah, it should be on the panel there.
Here?
Yep.
Okay, so I need to switch it on. Okay, why not a switch on the wall? Okay, so let me try to write this up. Yes?
What if we have an item which could possibly be grouped into different
Yes.
clusters?
Okay, we need to decide where to put it, but
On the basis of distance, it's the same algorithm.
yes, of course, in this case, you cannot choose, you just decide, you throw a coin, for example, You need to randomize the procedure in that case. There's no way. Unless you have other information, but here we only assume that we have similarities or distances between objects. So, the idea is that we start with, let's call C the collection of our clusters. Okay, let's see. Let's start by deciding what we are given. We have a set of items. Let's call the items well, let's call D the set of items. And we have a similarity function that is applied to every pair of items and provides, as a result, a real number. Of course, a non-negative real number, because we're considering, well, it depends. Actually, a real number. Okay. I call it S, so it stands for similarity. Two similar items will have a higher similarity. Two different items have a low similarity. So the similarity between 4 and 5 should be high, and the similarity between 1 and 5 should be low. Of course, as I said last Monday, if we prefer to consider distances, that's exactly the same. We only need to reverse all inequalities. So, a larger similarity means a smaller distance. And that's all that we have. Now, we build our set of clusters, and the first thing we do is, okay, we just consider the singletons. So, initially our set of clusters is the singleton of element D for every element in D. The collection of all singletons. So, C is a set of sets. And in particular, C will always represent a partition of D. Do you know what a partition is? So, it's a collection of subsets, so that every element of D appears just once in C. So, the union of all the sets of C is D, and two different sets in C have void intersection. Next, we want to repeatedly pick two clusters out of C and merge them together. So we need to repeat something as long as the cardinality of C is larger than 1. So, as long as C has more than one set, we will stop when C is just one set. Okay. Okay, other than this symbol, maybe let's use this. Okay, number of elements in C. We just find C1 and C2 in C. So we pick the two elements of C that are closer together. So let C1 and C2 such that, of course there are many different ways of writing this, the similarity between C1 and C2 is the minimum for all x and y in C. Okay, for example this. Of course, we have to improve this definition in many ways. For example, if I look at in general, if C is a collection of clusters, and I want to find the two clusters that are most similar, actually, well, a dirty trick would be taking twice the same cluster. So if C1 and C2 are the same cluster, then of course it's as similar as possible to itself. So I want C1 and C2 to be two different clusters in C. And also here, the two different clusters that are, I want to find the two different clusters that are closest to each other, that are most similar to each other. And of course, since I'm still talking of similarity, sorry, I have to consider the maximum similarity. Next, once I have found the two clusters, I remove them from C. So I take C1 and C2 out of C. This is the set difference. Okay. So I take C, I remove these two from C, and I add the set containing their union. Okay, I remove the two separate sets C1 and C2, I merge them together and I add them to C. So in this case, we can draw this a little more. So we start with C as a collection of singletons 1, 2, 3, 4, and 5. We identify the two elements of C that are closer to each other, in this case 4 and 5, so the two most similar. We remove the sets, the items 4 and 5 from C, and we add their union. Next, so we have C is composed by the sets 1, 2, 3, and 4, 5. We find the two most similar elements now in this set of 4 items, which are 2 and 3, and we remove them and merge them together. Now C contains 1, 2, 3, and 4, 5. Next, we repeat. We take the two most similar items, we remove them from the set and merge them together. So we remain with the singleton 1 and the rest of the elements in another set. Next, we find the two most similar, we remove them and replace with the complete set. Okay. Of course, if we let this procedure run from the beginning to the end, what we always come up with, okay, is with C containing as its only element D, because we have merged all elements together. So maybe we also want to remember the previous step so that we can decide when to stop or what is our favorite cluster. So for example, we can say, okay, here we call this, the set of singletons is called C0, for example. Then we maintain a counter, let's say I, starting from 1. And we define, so at every step we create the set of clusters Ci based on the set of clusters Ci minus 1. Okay, so what we actually have is C0 this, C1 will be the set 1, 2, 3, and 4, 5. The set C2 will be, of course, somewhere I have to increase I. One, 2, 3, and 4, 5. Then C3 is 1, 2, 3, 4, 5, and finally C4 is this set. Okay. Is this clear up to now? We actually have one problem here. You see, it's easy to define the similarity between two elements in the set. So, for example, if the elements are points on this blackboard, then the similarity can be 1 divided by the distance as measured by a ruler. So the most similar elements are 4 and 5 because they are the closest ones. Okay, but what about the similarity between the cluster 2, 3 and cluster 4, 5? How do I measure the similarity between not two elements but two clusters? Okay, let me repeat. Here, the only definition that I have is the similarity between elements in my original set. So in the set of items, or if these are documents, it might be their Jacquard similarity, for example. Okay, so we have always defined the similarity between two objects. We must extend the definition of similarity between sets of objects. So, mathematically, let's say, we start from a function that relates two elements in our set. But what we want to end up with is an extended definition, an extended kind of similarity that can be worked not between two elements, but between two sets, for example, by defining the there are so I want the similarity to work between two generic subsets of D. So I use this symbol to indicate the power set of the set. So the set of all subsets. So if I have two elements here, D1 and D2, I know how the similarity is computed, because the similarity between D1 and D2 can be, depending on how it's defined, can be, for example, the distance, or okay, of course, the distance is not a similarity, so I should make, for example, 1 divided by this, or the Jacquard coefficient if D1 and D2 are represented as the sets, or another definition that we saw is the dot product of D1 and D2 if they are represented as vectors, and so on. But if I have two collections of elements, how do I define their similarity? And here there are many possible definitions. So, okay. So the question is, given, let's say, D1 and D2 subsets of D, how do I define the similarity between D1 and D2? So in this case, I have two sets of elements, and I want to define the similarity between these two sets. For example, one possible definition is this. Let's consider the two elements, one in D1 and one in D2, that are most similar to each other. Let's take that one as similarity between sets. So two sets are as similar as the most similar pair that they contain. You can say it's the maximum for document D1 and D1 and document D element, okay, D2 and D2, of the similarity between D1 and D2. This definition recalls what in mathematics is usually considered, for example, the distance between two sets. In order to have the distance between two sets of points, you take the two closest elements, and these define the distance. So this represents how close the two sets are able to come to each other. Of course, if D1 and D2 contain one common element, so they are not separate, but they contain the same element, then of course the similarity is maximum because you take the same element twice. Or you can decide that two sets are as similar as the most dissimilar elements. So you take the two elements as far as possible in the two sets and you define that as set similarity. So instead of this, another definition can be the minimum for D1 in the first set and D2 in the second set of the similarity between D1 and D2. Another possible definition is, well, who cares about the maximum or the minimum? Actually, if we want a good measure of similarity, we could consider the average similarity between elements in D1 and elements in D2. So, we can take the arithmetic mean of similarities between elements in D1 and elements in D2. So, the sum for D1 in D1 and for D2 in D2 of the similarity between D1 and D2. So the sum of all possible similarities between one element in D1 and one element in D2 divided by the number of such similarities, which is the size of D1 times the size of D2. Okay. You consider all possible pairs of elements where D1 belongs to the first set and D2 belongs to the second set, and you take the arithmetic mean of everything. So this is the average similarity of the two sets. Another definition, the last one, well, we first need to define, given one set, D, what is, well, D is the complete set, let's call it, let's take D1 subset of D. We can define the self-similarity, okay, of the set D1 as the average, the arithmetic mean of all similarities between elements in D1. So, In this case, we take the sum for all pairs of elements D1 and D2 in the set D1. And divide it by the number of possible pairs of elements D1, D2, which is, in this case, let's say, number of elements in D, choose number of elements in D1 taken twice, because I'm considering every pair twice after in this case. Or one divided by, so this is oh, sorry. We don't care about the size of D. I meant to write this, okay. So all possible pairs of elements in D1. Which is this number here, sum. So, if we define this as self-similarity of one set, the average of all pairwise similarities within that set, then we can define the similarity between two sets as the self-similarity of the union of the two sets. So these are four possible definitions that extend the notion of similarity between elements to the notion of similarity between sets. So, we have seen different possible definitions of similarity between elements, Jacquard, cosine similarity, and so on, and different possible extensions here. Now, suppose that we have the initial example, okay, that I was giving. So, suppose that our elements are like this. How does our algorithm work? Well, in this case, the outcome is more or less independent of the choice of the similarity extension. What happens here? The algorithm starts by joining together similar elements And what we can actually expect is that at every step we are merging together clusters that belong to one of these three groups. The final steps should see three clusters here, and only when we have these three groups, then the algorithm needs to decide which two must be joined together. In this case, of course, depending on the definition, depending on the mutual position, it will decide that these two must be joined together, and finally, it will join these ones and stop. But at some point, we will find these three clusters clearly separate from each other. With this algorithm, well, we can represent the behavior of this algorithm in a more precise manner by drawing a diagram which is similar to what I've done before. So, let's see. Let's start with let's do a simple example. Okay, so like that we have three clear clusters, but for simplicity, let's suppose that every cluster is made by 2 points. Let me call them 1, 2, 3, 4, 5, and 6. Okay. Okay. In some sense, what the algorithm is doing is this. Suppose that we have a scale of similarity between elements. What clusters have the highest, so let's say the highest similarity in this is between each element and itself. So let's just write the elements at the top of this scale. So these are the 6 singletons that are the starting point of our algorithm. Now, our next step is find the pair with the highest similarity. So in this case, suppose that it's 1 and 2. 1 and 2, the similarity between 1 and 2 is of course lower than the similarity between every element in itself. So suppose it's this one. Similarity between 1 and 2. So let's say that the two elements, 1 and 2, are connected together at this level of similarity. And this corresponds to step 1 of the algorithm. Next, suppose that 3 and 4 are more or less as similar, maybe a little less similar. So we can draw them like this. So at step 2, 3 and 4 are merged together. Let's say this is step 1 of our algorithm. At step 2, we have merged together 3 and 4. Of course, at every subsequent step, the similarity between the two sets that are joined is less than the previous one. If it was higher, we would have joined them before. So the next step, we find the next most similar ones. And so at step 3, we find the similarity between 5 and 6, this, and we join them together. At step 4, okay, we start looking at similarities between these groups. For example, 1, 2, and 3, 4 are the most similar. So, for example, this is the level of similarity between 1, 2, and 3, 4. And so at step 4, we merge these together. Finally, at step 5, we consider the only remaining similarity, so between set 1, 2, 3, 4 and set 5, 6. And join them together. At this point, we have one large cluster at step 5. Okay, so this is a visual representation of what has been done. And in particular, in this representation, we can precisely define the level of similarity that was considered at each step. Okay, by the way, this kind of definition is called the dendrogram. Dendro is the Greek word for branch of a tree. And, well, I think so, but I'm not sure. You see that with this representation, we can also try to decide where we would prefer to set our clusters. I mean, you see, this diagram shows you all possible clusters, all possible clusterings of your set by just taking a slice of the diagram at your preferred level of similarity. So if you decide that you want, you see, all elements that are more similar than this to be grouped together, and all elements that are less similar than this to be in different clusters, if you take this section, you identify this clustering 1, 2, 3, 4, and 5, 6. If you prefer another level of clustering, for another level of similarity, for example this one, then this section identifies this different clustering. The cluster 1, 2, 3, 4 and the cluster 5, 6. Of course, everything below this level of similarity identifies just one cluster, that is the set of all elements. And by looking at this diagram, you can also see that, for example, the first steps were all on very close levels of similarity. So, steps 1, 2, and 3 implied a very low decrease in similarity, while the big step is between levels 3 and 4. So, in a sense, you can see that the best candidate for clustering in this case is what happens between in the middle of this large step. Okay, you see that up to level 3 you were merging things that were close together. The next step required a consistent reduction in similarity. At this point you understand that you were starting to connect things that are farther apart. So this is probably a good point to set your similarity level and to choose your final clustering. If you have many points, then you would have a similar behavior where a lot of the initial mergers are all with a high level of similarity. At one precise point, when you have these 3 large sets, the next merge would require a consistent reduction in similarity level. At that point, you can somehow see that your clustering is done. Okay. There is a precise point where you start joining clusters that are very different from each other. If you draw here the step and here the similarity of the elements that you are going to merge, you start with a high similarity, then somehow you find a sharp drop in similarity when you start merging clusters that are far apart. So you may find a way of deciding where your true clustering is. Let's look at another example. The other example that I have done before. So a long string of points and another group of points here at the center. What happens with this clustering procedure? Well, in this case, again, you start by joining together elements that are close together, okay? Now, what happens when you go on with this example? Okay, first, of course, you're going to merge all close pairs of elements. Like this. or also closed pairs of groups of elements. But at some point, you will end up with fairly large clusters that are, well, more or less distributed along this corona here, and maybe with one large cluster here. How does this proceed? So, for example, you could expect to end up with this large cluster and this. Will it happen? So, will this be the next to final step before merging everything?
Depends on what. If we choose the maximum distance between the points in the cluster, is different from the minimum because the minimum will do the corona.
So, it depends on how we extend the similarity. Okay, do you agree with your colleague? So it actually depends on how we define the similarity between sets. If we take the minimum of similarities, then of course we will get to, okay, these two sets will be merged together because their similarity is the similarity of the two closest ones. So we'll join these, we'll join these, we will join these. Then we will merge together sets based on their closest elements. So the next two final steps will be actually this large horseshoe and this at the center. But if we consider the other definition of set similarity, so for example the two farthest elements, then maybe we, considering the second to last step, we will end up with these three clusters. But when we want to join them, then the similarity between this and this are actually dictated by the two farthest elements. So it will be larger, smaller than the similarity between each of these two sets and the center. So in that case, we will end up with maybe this cluster and this cluster, and finally with the final one. So in some cases, the end result is actually dependent on how we define the distances, the similarity of sets. So, by the way, I don't remember if I told you the name of the algorithm. No, probably not. So, usually we call this the algorithm that starts with singletons and joins them together as hierarchical. Clustering. Hierarchical because, you see, what we are building is actually a hierarchy of clusterings from our set, starting from singletons and then going down. Another definition, okay, it can also be called agglomerative clustering. Agglomerating because we are actually merging objects together, or also bottom up clustering. we start from the bottom, from the single elements, and then we build upon them a structure of subsets, a hierarchy of subsets. Okay, so hierarchical, agglomerate, or bottom-up. Okay. So the other fundamental approach in clustering. Oh, by the way, as you see, this kind of clustering only requires us to define the similarity between elements. This means that this kind of clustering is only based on what we call an external representation. Okay. We don't need any internal representation of the elements. We only need similarities or distances between elements. So what we need in order to use this algorithm is a table of similarities, for example. Okay, we are never using any internal representation, any vector representation or so. We start with similarities between elements and we only use them. Maybe tomorrow we will see some exercise about this. If we have a vector representation of our elements, then we can use other methods for clustering. So, in the next part, we will suppose that our set of elements D is actually a subset of some n-dimensional vector space. So the element D is actually a vector D1. Dn. Okay, this in this case we can rather than just considering clusters as sets of elements, we can take a different approach. So suppose that we are in a vector space and we have a set of elements here. And we ask ourselves, can we remove these elements and replace them with a single representative? And in that case, what is the representative that represents them best? For example, if I have this set of elements, I may choose to represent them with a single element that is more or less in the middle of them. By saying that this is reasonably similar to each of these elements. The fact that I have an internal representation allows me to create this element from scratch. So I don't need to take one of the existing elements as a representative. But I can create another one, because I have an internal representation, so I actually create a new vector. And so suppose that this is our set D. Let's call the elements D1, D2, and so on, and we know that they are vectors. So our set D is made by let's say it contains L elements. My question is, I want to replace D1, DL with a single vector, let's call it move, in the same vector space, because all these belong, of course, to such that this vector approximates these elements as well as possible. Let's define what I mean by representing them as well as possible. Well, I mean that you see, I'm well, in a sense, if I replace document D1 with vector move, I'm introducing an error in my document representation, which can be measured as the distance between move and D1. So, what I'm actually doing is introducing an error E, depending on how I define move, which is given by the sum of all distances between DI and move squared. We usually take them squared for simplicity. So I want to replace these documents with these elements with one single new element, so that this error is minimized. Okay. Let's see how we can minimize this error. Well, it's rather easy actually. So let me write this. So the error for when choosing move is can rewrite this as sum for all indices from 1 to n, n is the dimension, of the squared difference between the kth component of di and the kth component of mu. Okay, this is the definition of the two norm. So if I want to minimize this P of mu, I know that mu is a vector. I just need to take all the derivatives with respect to the vector components and set them to 0 for all index k. Okay, if I want to minimize this, I have to find the stationary points of my function. Okay, let me rewrite this by expressing this square. So we get dik squared minus 2 dik mu k plus mu k squared. Next, let's call J the index with respect to which I derive. So, of course, the derivative with respect to mu J of course it can go inside the sums. So finally this is derivative is sum for I going from 1 to L. Here we have a derivative with respect to mu J. So all elements that do not contain mu J contribute 0 to the derivative. The only element that does not contribute 0 is the one where k is equal to j. So it's actually the derivative with respect to mu k of, so to mu j, sorry, of dij squared minus 2 dij mu j plus mu j squared. Okay. For all other values of k, the derivative is 0. And this is sum for e going from 1 to L of, we can derive simply the three terms. The first term does not contain mu j, so it's constant with respect to mu j, and the derivative is 0. Here we have 2 dij plus 2 mu j. This is equal to, and we want to set this to 0. So finally, if we take, okay, here we get 2 times, okay, the sum for I going from 1 to L of dij plus, okay, we sum L times this, so we get 2L mu j equal to 0, which gives us, by simplifying things, that, oh sorry, this was minus here, here. So finally we get that mu j is equal to 1 divided by L sum for I going from 1 to L of d I j. From this we get that the vector that best represents a set of elements by minimizing the sum of the squares of the distances, so the element that is somehow closest to our set of elements is the arithmetic mean, the average, the centroid of our set. So, so we get that the vector that minimizes this error is the vector that we obtain by computing. So this is exactly this equation for j going from 1 to n, so in vector form. So if we have a cloud of points and we want to replace them with the vector that best represents them, we have to replace them with their average value, their arithmetic mean value. Now, this of course is true if we want to replace all our points with one single point. Then that single point should be the average. What if we are trying to replace this with a set of representatives? So the idea is, suppose that we want to cluster, to divide our set D of elements into 3 parts. And we want to represent each of these parts with one single vector that best represents that part. So the problem that I want to solve is this. Okay, we still have elements d1 up to dl indeed. And I want to find k vectors mu1 up to okay, each of them still in Rl. So that, so I have L elements. I want each of these elements to be represented by one of these vectors. And in particular, I choose for each element the closest vector. So, let's say, given the element pi belonging to our set B, okay, I would say that pi is represented by vector mu j such that the distance between element di and vector mu j is the minimum between I'm starting to miss the indices. Or L, no, L is that one. So at present I'm using I, J, K, L, M. Okay, I want to find for every element in my set, I want to find the vector mu that is closest to I, to the document pi. Oh, I still need a little more make the notation a little more complex. So let's say that Ji is the index of the mu vector closest to di. So, I want to find, given my L original elements, I want to find k vectors. Of course, I want few vectors that represent a large number of documents. So that, if I consider the overall error, it's minimized. What error am I considering? The sum of all distances between all elements di from their closest representatives mu. So I want to find the k vector such that this is minimized. if you want, this is a generalization of the previous definition. Before, I only wanted to find one move that best represented all elements. Now, I want k different vectors, and so that if I replace every document with the closest of these k vectors, I still minimize this. Of course, if I have the usual set of elements like this, it's clear that the I set k equal to 3, so I want to find 3 vectors that best represent these points. My objective is to place the 3 vectors at the centers of these 3 loops of elements. Okay. Okay. Next time we will see some algorithms to make this more or less formally. Maybe tomorrow we will see some exercises and some both paper and computer exercises about the previous topics, okay, up to the hierarchical clustering. And then next Monday we will go on with this. Okay, I think that's all for today.